So what it says is, does the cat create the moon by observing it? And the point of today's talk is to tell you something strange about what everyone knows. That's quantum mechanics, which works perfectly well, and that's our best theory for describing the world. The most precise one, well, in the guise of quantum field theory, of course. At the same time, it doesn't explain itself. And now we are starting to wonder what quantum reality is and what quantum computer is and everything. So the title is Quantum Reality and Quantum Computer, the most general overview. I'm Alexei Semikhatov, and the spoiler is that quantum computer is not a computer. It's an analogous device for growing the wave function. And quantum reality is somewhat elusive notion. It hides behind measurement and collapse. And here's a quotation by David Deutsch, which I will have to, I'm sorry, I will have to translate it back into English with limited success. Despite the unprecedented empirical success of quantum theory, the very idea that can literally describe reality is met with, how do you say it, mistrust. Dima, you help me, mistrust, misunderstanding, and even wrath. David Deutsch is one of the founding fathers of the idea of quantum computing, as you probably know. There will be several chapters. The first is quantum mechanics, as if you have never heard about it. As if you're a general audience, which is sometimes a fun thing to pretend you are. Quantum mechanics at the level of a metaphor. And wave function is, roughly speaking, for someone who have never heard about it, is putting all the possibility into one pot at once. And the metaphor of the wave function is a playing card, which is a very special playing card. It can only exist as a metaphor. It doesn't have a particular value. There are several values which live together in a single playing card. This is not a stack of cards. It's a single card without a definite value, and despite the plus here, the 3 and the 7 never add up to a 10. So every single value maintains its individuality, which is very important, and to ensure that we protect them with cat brackets, and every kind of possible value which coexist, all of which coexist there in that single card, they can be associated with certain numbers. So numbers can be placed like that. And a not metaphorical but a real wave function, something like that, the R1, R2, etc. points of space, you will tell me that they're continuous, so there is no summation, there is something more complicated. That's totally true, but I really don't care. The idea is there, that's a linear superposition, and this is something with arbitrary numbers. That's superposition of general positions in space. It doesn't describe let's say an electron located in a particular point of space. It does not do that, and different points of space are present here just as if they are just mentioned, and the mention of every one is associated with its own number. And then now that you were given that playing card with very special properties in my casino, to which I invite you, we are not for card play casinos here. We're not advertising anything, so that's a disclaimer. But in my casino, you have the opportunity to play with other visitors, and any communication is an interaction. So that's a metaphor of an interaction. Playing with other visitors is a model of an interaction, and I have very simple rules. If I have a red card, then yours become a king, and if I had a black one, yours, that's your card, yours becomes a queen. Now the point is, what do you have a superposition of cards, and then by the rules of quantum mechanics, this is as my card and this is your card. Then your card reacts to both opportunities, both possibilities that were kind of hiding in my very special card without a particular value, to the two that I have here your card reacts with a king to the red one, and to the black one your card reacts with a queen, and where therefore are entangled, and neither my hand nor your hand can be described in definite terms, even though our hands together, the two hands together, just are perfectly well described by this combination. There are not 4 but 2 cards. Mine goes first and yours goes second. That's it. And an important point about the wave function is that when you have a system of, say, 2 electrons, you don't have 2 wave functions, just the opposite. You have a single wave function for all quantum objects that you have. Once again, that's a metaphor. This is there are 2 cards, mine and yours, and they have correlated values. Something like that, and the not metaphoric but a kind of real wave function of 2 quantum objects is that when the first object kind of think of sitting in a point R1, which it doesn't, the second one, the other is kind of thinking about being at a point S1, and that thought, so to say, that possibility is associated with number A1 and so on and so forth. And an important point, of course, is that there are pairs. Every number A1, A2, A3 is associated not with a single point in a physical space, but with a pair of points. So when you have a quantum system of 3 objects, then you associate a number with 3 points, which means that the wave function is not a field on our space. So it's neither a wave nor a function on the physical space. It's only defined on the configuration space. And as we all know, wave function evolves following the Schrödinger equation, and the Schrödinger equation, a teaser of the Schrödinger equation is that energy tells the wave function how to change in time, and it does it in this particular way, where h is the Hamiltonian, which is, think of it as an energy depending on canonical coordinates, turned into, there are a lot of subtleties about what's written here, but anyway, turned into an operator like in coordinate representation, something like that. I skip actually a big chunk of science. So it's a linear equation, and it's a deterministic evolution. So we associate quantum mechanics with indeterminacy, with probabilities, but they're not here. That's a deterministic evolution. We know the wave function now, we know the wave function at any moment in the future, as well as any moment in the past, and as long as the Hamiltonian is Hermitian, your evolution is unitary. And once again, the wave function here is a function of the configuration space. The contact with reality. So the wave function is not observable. I will tell about it later. I will say about it later. But the contact with reality, how we experience, what this description is for. We experience it when we make a measurement. In my funny casino, the rules are that a bouncer comes to you, approaches you at a certain point. That's a gentleman you can hardly refuse following his suggestions in a casino. So that gentleman comes to you and suggests that you show him the card. And you show the card, and when you show the card, it just becomes, the casino makes your card ordinary. Instead of being a linear combination of different values, it becomes a single one. It can be whatever. It can become any one of these that were kind of contained in that single playing card that you had. If you don't have the ace of clubs here, you will never ever get an ace of clubs here. So it can only turn into something that it kind of contained. It used to contain before the guy from the casino asked you to show the card, to present your card. But the result is never predictable. You don't know which ordinary card it will turn into. But then if you keep doing that, repeat that many times, you observe that there are certain probabilities. And there is a Born rule, that's Max Born, who, as a matter of fact, like some of you do, started studying Russian language when it was time to leave Germany after 1933. Kapidza invited Max Born to Moscow, and for a while he considered the proposal and even started learning Russian, but didn't actually get very far in learning Russian or in coming to the Soviet Union anyway. But what the Born rule is telling us anyway, so that's Max Born, what Born rule is telling us anyway is that the probability that you observe a 3, you have to take this number that stands in front of the 3 and square the modulus and do that the same with every other card. And that was in my casino, which is not a real thing, of course, but in real life, what happens is that that's the wave function, say, of a single electron, and even it's a little bit oversimplified, but anyway, so an electron with probability, the same rule that you take the modulus squared of this number, and it can find itself, I will specify the term in a moment, at a point R1, or at point R2, or at point R3, anywhere in space. The only thing is, what does it mean that an electron finds itself? When it happens, because the wave function used to evolve guided by the Schrödinger equation. So what happens here? There is no casino in the real world. The claim is that instead of the bouncer in my casino, what plays about the same role and what imposes something new, some unusual behavior on the wave function is a measuring device. And the measuring device, the wave function collapses, loses all the possibilities and reduces to a single one when it's measured, when we use a measuring device to find out what's there in the world. So interaction with the measuring device just does this. It selects a single possibility, and the wave function and all the other possibilities are no longer there. So they just disappear, they just vanish. The possibilities that didn't occur this time vanish from the wave function as well. So the wave function reduces this collapse because it's called collapse because there used to be anything what was in principle possible, but no longer there is just, it reduces, collapses to a single possibility, the one that occurred this time at this measurement. That sounds rather logical, but the problem is that, remember what was the case with our cards. According to the Schrödinger equation, what written above this arrow is the Schrödinger equation. Interaction results in an entangled state, like this one. So interaction is also, measurement is also an interaction. So you're supposed, according to Schrödinger equation, you also have to get an entangled state. So here is the device in a ready state, and the Schrödinger orientation. So that's an electron, spin up and spin down, linear combination. And what happens, according to the Schrödinger equation, is that my device should tell me that, yes, I detected spin up, that Stern-Gerlach device, for instance. So to the possibility, to the part of the wave function that is spin up, my device has to reply with, yes, I detected spin up. And to the part that spin down, my device has to reply with, I spin down. I skip some reminder about what the spin of the electron is. And it is here that Schrödinger decided to make it more dramatic and added the cat. That was in the previous era, when the rights of animals were not protected as strictly as they are now. So he was free to say that he also involve a cat. So the third cat vector is for a cat. And the cat first is sleeping, and then you actually, that has nothing to do with quantum mechanics. Quantum mechanics is certainly not responsible for that. You just, there's an optional, you buy an optional device that injects a very fast-acting poison whenever the device measures spin up. So in that case, when it measures spin up, nothing to do with quantum mechanics, but the cat is dead. But then the cat is also, of course, consists of quantum objects. It's also involved in the superposition. And when the device measures spin down, that's spin down and that's the device measuring spin down. Nothing bad happens to the cat, it's just enjoying itself. So according to Schrödinger equation, we've got to have an entangled state, but even Schrödinger understood that in reality we have collapsed not entangled cats. All our cats are collapsed, not entangled. So which means that Schrödinger equations no longer followed, is not satisfied when we make a measurement, which is a real weird thing. Now we'll just recapitulate that in a little bit without appealing to my fictitious playing cards. Wave function is an element of Hilbert space. We have a Hermitian metric, which is Hilbert space means that it's positive definite. The most important thing is that it's linear. We have the superposition principle. And the very important point is there is no preferred basis. That's a big deal, actually, because when you start learning quantum mechanics, you always have somehow natural basis. But a spin is a very good illustration. So if you, for some reason, decide to describe the world in terms of spin up and spin down basis, that's a basis in a two-dimensional complex space where the spin lives. But then this particular linear combination is just a single state spin whatever to the right. And actually any linear combination can be expressed as a single state spin directed along a certain direction in space. So there is no preferred basis, and that's it has a bunch of consequences, which I'm not going to discuss, but that's an important point. And as I already mentioned, the wave function is defined not on the physical, but on the configuration space, on our R3n. It has no particular value, no value at a given point in R3. That's Heisenberg and Niels Bohr criticized Schrödinger in very harsh terms. That's a bad thing. He had nothing to reply. But we still have nothing to reply to that criticism. But it works. It doesn't matter. And as I said, the wave function describes the system as a whole, not its elements. So one of the consequences is entanglement. And I mentioned that briefly, the wave function is not observable. There is no procedure. So given a wave function, there is no procedure, and that's choosing some basis in a Hilbert space. There is no procedure even in principle to determine the coefficients alpha, beta, and gamma, and so on. So the wave function evolves deterministically, guided by Schrödinger equation. Schrödinger equation is linear, and that's enough for creating entanglement. And the evolution is time reversible and even unitary. The indeterminism comes when we do the measurement. I'm just repeating what I've already said, so I can skip this. We get one of the possible values. In the simplest case, there are more sophisticated measurements, positive operator valued measures. But in the simplified version, this can be eigenvalues of a Hermitian operator, which corresponds to some physical quantity, and with Borner rule tells me what the probabilities are. And of course, in a most general case, you have to take the scalar product, and then you have to normalize and everything, so I will skip that. Now, when you do the measurement, it's associated, it comes together with a collapse. The wave function collapses, and to one of the particular basis states in the basis that you were making the measurement. That's a very important point. That's a stochastic process, so it cannot be described by deterministic Schrödinger equation. And there is some subtle non-locality. Like, for instance, when the wave function is of this form, these certain A, B, and C can correspond to spatially separated regions. So a millisecond ago, there was a possibility to detect your electron or photon, whatever, anywhere. And then suddenly it's in this particular location, which means that instantaneously, at this very same moment, it's not in any other location. So there is already there is subtle non-locality in quantum mechanics. Now, the quantum mechanics does not describe its own use in the way that it doesn't describe how Schrödinger equation is violated. Is it replaced with anything? Is there anything that, for how long time it's separated? It doesn't even describe what a measurement is. So you would probably say that things would become much more clearer if I tell you what a measurement is. Quantum mechanics doesn't, in no way does quantum mechanics specify what kind of actions qualify as measurement. nor does it say what a measurement device is. But it does say in a standard interpretation that the measurement device has to be classical, because if it must not obey the Schrödinger equation, because if it does, if it were obeying the Schrödinger equation, we would get the Schrödinger cat and we would get all possibilities. There would be no collapse because we would just get entangled states. So that's the way that the measurement device telling me that I measured spin up, I measured spin down, should behave if it were obeying the Schrödinger equation, but it doesn't. Which is a weird thing, because the whole device is composed out of electrons and photons, protons and neutrons and everything, which are quantum objects. And you can now also ask the question even in a little bit more sophisticated manner, how does a single electron whose spin you measure, how does it know that you for instance, or we together, decided to measure the spin of that electron along the vertical direction or along horizontal direction? How does it know? Because it only sees something very local, some parts of the device which are about the location of that electron itself. How does it recognize that it is now in a measuring device and we are measuring something particular? That's another quotation which I'll have to back translate by Murray Gell-Mann. That's from his Nobel lecture. And what he's saying that Niels Bohr brainwashed a whole generation of theoretical physicists, making them believe that the problem of finding interpretation to quantum theory has been solved 50 years ago. That's my back translation, very close to the original. You can search for it on the net. That's no more no less than from Nobel lecture by Murray Gell-Mann. Now, in my title, that was kind of extended introduction, which is already growing into early conclusion. But in the meantime, I had the word quantum computer and quantum reality in my title. So let me tell you something about how strange quantum reality is. As you probably know, non-commutativity forbids you having properties at the same time. So the two properties are hostile, they are not friendly, and there are a pair of hostile properties which cannot be assigned simultaneously. Like position and momentum to an electron, which of course means that there is no motion along trajectories. Yes, a trajectory is not a real line, it's kind of imaginary thing, but still our intuition of Newtonian mechanics is that a stone, a planet, everything that we can think of moves along a certain trajectory, which at least in principle can be known, not so in quantum mechanics, just because of the non-commutativity of coordinate and momentum. And the situation in a stationary atom is that because the position, because of the Coulomb potential term, the position does not, because of the kinetic energy term, as a matter of fact, because of the kinetic energy term, the position does not commute with the Hamiltonian. Which means that an electron which is stationary in an atom has no single position in space. The electron in an atom has no property of occupying a single point of space. At the same time, we know very well that an electron is a point-like object. So this is something which quantum mechanics never explains what the electron is doing. It doesn't bother with that sort of questions. Quantum mechanics also going to tell you what the probabilities are when you make a certain measurement, and then its predictions are very well tested. But don't ask silly questions about what quantum objects are doing when between observations. So this is kind of existence which is indeed very difficult to imagine, kind of unimaginable, unperceivable way of existence. Not all properties, not all features can be attached to a single quantum object simultaneously. They can be attached to it one after another, but some of them cannot coexist. The results are very crucial for our existence because of the kind of tension due to non-commutativity. It's very difficult to make a nucleus and electrons live together. You can only do that in just a discrete number of cases. And that's why an atom of a single element is always the same. Well, of course, it can be excited. I'm talking about the ground state and not talking about what happens in the magnetic field. Just an atom left by itself in a ground state. It's always the same. It can lose all of its electrons and then it can be given electrons back. It will be non-distinguishable from what you had before. Actually, all of the periodic table and all of chemistry is a product of that quantum tension due to non-commutativity, as a matter of fact. Then there is a funny thing about quantum world, which is not so popular as non-commutativity and the ensuing indeterminacy and everything. That is, in many cases, in some cases at least, it's impossible to have predefined answers to certain questions. That's the Kochen-Specker theorem, which I will talk about now. In simple terms, in layman terms, it means that when asked questions, when ask a system a question, the answer from the system depends on what other questions I'm asking at the same time about totally different things. That's called contextuality. So I measure a property A in two cases, together with properties B and C, and together, that's case 1, and in case 2, together with properties C and D. And this triple are all commutative, so they can very well exist simultaneously. And this triple also, all of them pairwise commute, so everything is fine. Now, all the properties, A, B, C, D, E, the whole list, they're independent from one another. And here's the thing. There are cases where the quantity I'm interested in, A, cannot have a predefined value in a system which would suit both cases, which would be suitable for both case 1 and case 2. I will illustrate that on the next slide. Which means, in simple terms, as I already mentioned, that an answer to a question depends on what other questions you are asking about totally different things, about unrelated things at the same time. That Kochen-Specker theorem, it was published in 1967, and already in 1960, Specker wrote that he knows the theorem, and his motivation is very funny. The motivation is whether the how would you say that? All knowable of God, not omnipotency, but the fact that God knows everything, does it extend also to the events that would have occurred if something had happened which actually had not happened. That's a very good motivation, but theology apart, Kochen and Specker proved the theorem, and Bell proved its own version, a little bit more clumsy, but with roughly the same conclusion in 1963. And here is an example: Asher-Paris. These two names are Asher-Paris and David Merman. Paris-Merman square. So you have nine measurable quantities, ABC, small ABC and alpha, beta, gamma, each of which can take values plus or minus 1. And now here's the thing. In classical world that doesn't matter, but in the quantum case, which will later in my slide, every row and every column are commutative. So in a context, these are variables that can be measured at the same time, every row in every context. Now, classically, assume that these values take some arbitrary values, even they can be random values. I have six products along every row and along every column. So these are 6 products. ABC is the first row, C gamma is the last column. You see, every letter enters 2 of these triple products in this list. So there is an even number of products is equal to +1, which means that what I can do, I can say suppose these are randomly distributed variables. I introduce the probability and take the average, the probability of a particular product that I'm interested in. I do that for everyone, being +1 or being -1. That's the expectation value. So there is still some remnants of the English, unfortunately too scarce. But anyway, what happens is that classically you very easily convince yourself that if you have pluses, 5 pluses and 1 minus, this thing can never take a value more than 4. You can either list all possible cases, or you can realize, you can assign some values and then see that it's 4, no more than 4, and then changing the sign would always change the sign of any of these variables would change sign of 2 terms here. So the net effect is that it doesn't do anything to this. Now here's the quantum case. In the quantum square, you take the product of complex two-dimensional spaces, and you have Pauli matrices acting there. It turns out that this quantum square satisfies all the properties that I've declared. Every row and every column is a context. They commute. Well, they do. Now what happens is that you take the product and you realize that you have these values. So no matter what wave function, no matter how you define the expectation value for any state, this is 6. The same thing that classically could not be greater than 4 in quantum mechanics is 6, which means once again that you cannot have in quantum mechanics, for this to be the case, they cannot have particular predefined values. There is no way to as long as you distribute any values, you get this inequality. The actual Kochen-Specker theorem is in dimension d, starting with 3. That's the point. I think I will skip it in terms of, or maybe. So what do? You describe. You take rank one projectors, which are orthogonal, pairwise orthogonal, and of course there is a completeness requirement, and then you reformulate it in a very convenient way in terms of true-false statements. Like 2 statements must be jointly exclusive. They cannot be two different, cannot be true simultaneously. This is analogous to orthogonality of the projectors. And then not all of them cannot be false. At least one of them must be true. And now it turns out that what Kochen and Specker did, they in dimension 3 they presented 117 vectors among which you cannot distribute the true and false values such that these properties hold. That in no single pair of 2 orthogonal vectors both would be true. So this statement is: I forbid this case. I forbid the situation where I have 2 orthogonal vectors and both are true. And I also require that in any triple of orthogonal vectors, at least one take the true, given the true value. In dimension 3, you start with 117. I don't think it's been significantly reduced, but in dimension 4 there is a very nice picture. So here is the thing: every single segment of a line, like this one, or like that one, or this one, or this one, or this one, is a context. These are it contains 4 orthogonal vectors, and the actual vectors in 4-dimensional space are written here. Now, this ellipse is also 4 orthogonal vectors. The point is that you can check that those which sit on any given ellipse are also pairwise orthogonal. Now, I call every one of them a context. I have 6 plus 3, which is 9 contexts, and which means that according to my rule, I have to assign true value to 9 vectors. 9 contexts, 9, everyone has to have a single true vector. I have to assign, but every vector, everyone participates in 2 contexts. So the number of true values must be even. So that is contextuality, which means that even in the cases where you can somehow speak or assign quantum variables any values that are not directly related with what you observe, these are not what you observe. This affects, for instance, the de Broglie bomb interpretation of quantum mechanics, where you have hidden variables, but they're contextual. They are never literally coming from quantum reality into our reality. What do you do when you have some hostile environment, difficult to access? You send trained personnel there, like cosmonauts into space and quantonauts, I don't know how to call them, into quantum reality. And so to study quantum reality in more detail, can we send a man? Can we send man into quantum reality? That's the famous Wigner's friend story. Some of you may be aware of it. And here's the thing. Wigner's friend asked the questions whether or not things happen the same for different observers. So here's the story. Wigner, this is Eugene Wigner. He's a Nobel Prize winner as well, not for this contraption, for something else, as we know. But he also became rather famous in the combination of Wigner and Wigner's friend. So what Wigner does, it asks his friend to go to a laboratory and measure a spin of an electron, the spin of an electron in that state. Then the friend, here's the friend, she's in the laboratory, and what Wigner does, he isolates the laboratory from the entire world and considers his friend and the whole laboratory as a quantum system, of course. From Wigner's point of view, he's making no measurement, no nothing. He's just sitting idle. He's not doing anything. At noon, he is sure that the colleague has already received the electron coming in that spin state, coming into her laboratory, and certainly, viewing the whole system as a quantum system, Wigner is sure that the wave function of the colleague and the laboratory and the electron is this: to spin up the whole contents of the laboratory, including the mind of the observer and whatever she wrote on a piece of paper, is that the friend sees spin up. And the state of the whole thing, there is also a second part of the wave function. To spin down, the laboratory must react in a way that the friend sees spin down. There is no collapse, because that's Wigner's point of view, and he's doing nothing. No collapse, no measurement, no nothing. But later that day, when they meet at dinner, his friend is telling him that by noon she had already observed a particular result, for instance, spin down. So there is some inconsistency between what Wigner believed things were and what she told him things are. Are facts the same for different observers or not? Deutsch and in 85 and Bruckner more recently added some twists to this story. Like Deutsch suggested that suppose I make a very special window in the laboratory. Anyone reading Hungarian? No? Wigner was originally from Hungary. So that means I've observed a certain result. I observed a certain result. So I see a definite outcome. So what she's telling him, there is a very particular, if the knowledge from what she observed escapes the laboratory, that would affect the collapse of Wigner's wave function here. that alone. But she prevents that from happening. And what she does, she only tells him that I have observed a particular result. So Wigner is indeed in a difficult position because he trusts the observer, he trusts his friend as a qualified observer, and her observation and his observation definitely in real time are in conflict. There is also another twist of the story, a very recent one, that it turns out that the observer, the friend, has memory problems, because Wigner is asking her to do to follow 3 steps. First, she measures the spin of an electron in that state. Of course, she obtains the result either spin up or spin down. To her, the wave function collapses. We certainly know it does, which means that after that, the electron is an eigenstate of the spin operator. But then she's idle. And Bell does nothing. And what Wigner does, he makes a Bell measurement. The Bell measurement distinguishes between 2 wave functions. The one wave function that he's sure the laboratory describes the laboratory, spin up, observes spin up, spin down, observes spin down. And the same with the minus sign here, which is not the case, because we used to have the plus in the original electron spin wave function. So what this Bell measurement does, it confirms that the wave function is just this one. It in no way changes the wave function. It doesn't violate the wave function. There is no collapse actually. It just confirms, because it measures it's an eigen. Actually, this state is an eigenstate of this Bell's measurement. So what happens is that the state of the laboratory doesn't change. But then they had agreed that after a while, the colleague, the friend, his friend, would again make the spin measurement of the same electron, which after the first measurement is in an eigenstate. And it turns out, if you calculate the probabilities, which that's what Bruckner and collaborators did, that the friend has a problem. Let's say this P, A, and B be the probabilities that she observes A now that she had already observed B. It turns out, the calculation shows, that something happens to her memory or something or to something else. Even though the electron remains in an eigenstate, the fact that Wigner did a measurement in the meantime, which changed nothing, apparently changed nothing, leads to this paradoxical result that she has in 50% cases, she either doesn't remember what her first measurement is, or something else is confused in some other way. Which means actually that past events are difficult to include with the present events into a single picture of the world. The title of the paper is a no-go theorem for the persistent reality of Wigner's friend's perception. So she does have persistent reality because when Wigner does a measurement in the meantime, something happened to there is kind of rapture. Some kind of rapture occurs in her reality. We would like, of course, to make an experiment. You certainly understand why the experiment is impossible. Because you cannot isolate. Because what the environment does, the environment creates the classical world for us. And the environment is is a lot more than residual atmosphere, gas, whatever this Earth's magnetic field. These are solar and galactic neutrinos and cosmic microwave background and everything. Quantum computer is a device. I want to be a little bit dramatic. The story is about life and death of the wave function, because that's what we are playing with in quantum computer. Quantum computer is, as I said, analogous device for growing the wave function of qubits. The thing is that we only know about qubits. It has 2 well separated states. Theoretically, it really doesn't matter what they are. I'll skip the list. And we don't know what the best qubit of the future will actually be, because competing companies and approaches, they are developing it in different directions. There are mesoscopic states, there are artificial atoms, whatnot. So when I have it, so the point is I will keep talking as if it were an electron spin, even though there is no such quantum computers. The only thing is that my one elementary qubit is an elementary part of quantum computer, which has two basic states, and therefore in a linear combination, when I have two qubits, a linear combination, of course, the general linear combination, of course, 4 states, then 8 if I have 3, and of course we know what 2 to the 50 is, and we know what 2 to the 100 is, and that's why already 50 qubits make quantum computers interesting. But wait till we see whether or not it works. Computation is a wave function evolution, and it's a transformations of wave functions which are done by what is called gates. And the gates involve either a single qubit or a pair of qubits. And the big story, of course, is that depending on how you actually implement a quantum computer, it's more easy or more difficult to perform a gate when the qubits are spatially, physically separated by some distance. So I really don't care about it. Just being purely theoretical. That's Hadamard's rotation, maybe 1 over root 2 should be here, which is not. The most important, the very widely used thing is C0, which we know very well from ordinary programming, which means that when I have the first spin up, it doesn't affect the second kit, nothing happens. But when the first state is spin down, it does swap. It flips the second kit, and of course C0 produces the maximally entangled state from something which is not entangled in just this way. All gates which perform these and other transformations are unitary, reversible, unitary, in accordance with Schrödinger equation. And here is the way they draw what quantum computer is doing for you. This is not a real quantum computation, but anyway, any horizontal line is kind of qubit. This is Hadamard, this is some other transformation, and this is this C0, which actually does entangle different qubits. So the way you apply these transformations is a quantum algorithm, and the algorithm ends with a measurement. So in the end of the day, you measure your wave function, which means that it's no longer a linear combination, just a single result. And of course, the execution of the algorithm must take you to the answer, to the wave function that kind of knows the right answer. So I have a toy example here, and I have 3 qubits. I encode 8 numbers, of course. And whenever I have a wave function like this must be the correct answer, which is 7 in my case. It's only of course, when I make a measurement, any result I can obtain any result. It's that the one that is the correct one must have the higher probability. So I repeat the same computation sufficiently many times to make sure that I do get an idea of which result is the correct one. Like in that particular, in my toy example, this is probability 0.9, and this is probability 10 times lower, and this is another 10 times smaller. What collapse does at the final measurement, which can be only a single one, it turns qubits into bits or bytes. Qubits become bits only when you do the measurement. And the final measurement is the death of the wave function and the end of Schrödinger evolution, because as we discussed, measurement violates Schrödinger's evolution. And only one single measurement is possible, the final one. So, which raises a very interesting question: how about debugging? How can you control what's going on in the quantum computer? Because the whole thing is very prone to errors, and I will discuss that in a moment. Well, I'm already discussing it now. We know what classical errors are. Classical errors are just swap 0 and 1. And we know how to deal with this. The internet wouldn't have been working hadn't we invented a lot of tricks. The simplest thing thing is just to triple the information. We send 0 as 3 zeros and 1 as 3 ones, and therefore when there is a single flip, we interpret it correctly. When there are 2, we don't, but there are also more sophisticated schemes. Quantum errors are more diverse. An analog of this classical one is the quantum where you just flip the state. But there is another one. You can acquire a minus sign or actually any phase. First you think that it's a catastrophe because there is going to be any phase. But because there is a certain Pauli matrix which generates a flow for you, you can very well deal with just this minus, and it's already described. This is generic enough. A minus turns out to be generic enough, even though of course it can acquire any phase. So now there is no cloning theorem. You cannot copy an unknown wave function without destroying the original. So nothing of this sort would do. And before 1994, I think, there was total pessimism about the possibility of any quantum computations, just because of the no cloning theorem. You cannot do a trick like this one. So you cannot copy an unknown wave function. And of course, you cannot look up how my computation goes, because taking a look at what's going on means making a measurement, and then you destroy all your computation. So it was saved by entanglement actually, but it requires auxiliary qubits. You have to a single qubit in that state, you add 2 more qubits, prime and 2 prime, and you construct that entangled state. And now this effectively doubles or triples the information for you, because what you can do, you can observe the states, and there are tricky ways to do that, observe the states of these auxiliary qubits, and therefore get some idea what's going on in the qubit that you're originally interested in. It turns out actually that 3 is fine just compared with my classical example, but in the matter of fact you have to have at least 9, and then you start realizing that the auxiliary qubits are also qubits. They're just the same qubits, so they're also prone to the same errors. Their fidelity is not 100%. It's never 100%. So they also can have errors, and they also need auxiliary qubits. And the auxiliary qubits also would probably need auxiliary qubits. Then the gates, not a single gate. Gate is also a physical system which never works with 100%, never 100% reliable. So there is some level of errors. And the final measurement also occurs with some error. So the current situation is that, taking all that into account, all in all, to emulate an ideal qubit, you've got to have about 1,000, in order 1,000 auxiliary qubits. This is a big deal. It's a story, because the most pressing question at the time is how this scales, how the situation scales when you really want to have. It's fine when you have 4 or 5 or I don't know how many ideal qubits, but how it scales when you have 50, when you want to have 50 ideal qubits, we still don't know. It was either Google or IBM, I don't quite recall now, that last fall they made an announcement that they no longer, for them, the number of qubits is no longer a benchmark. They're benchmarking on how they can correct errors. So they realized this problem, and they said that we are now concentrating not on the increasing the number of qubits, because what we want to do, we want to be able to emulate ideal qubits. So why quantum algorithms sometimes can be better than the classical ones is the story is just because the wave function contains everything at the same time. Grover's quantum search algorithm is that there are numbers, and you want to pick up a single one satisfying a certain property. There is an oracle that you can address, but you don't know in advance which number does satisfy the property. So what you do, you take sufficiently many qubits so that you can realize all your numbers, and the number you're looking for is defined by a function f, which is 0 on all numbers except 1. On a single number, x star, your function f takes the value +1, and you need to find it. And classically, there is little you can do, really little you can do, but to check the numbers one by one, which means that there's O of n steps. It can be the average value would be half of the n, but you can be unlucky. Anyway, it's O of n. Now, quantum algorithm works this way. What you do, you first take a totally balanced state. All the numbers that are in the game are now loaded into a single wave function. Of course, it contains the one that you don't know, that you need to find. But the oracle that you are asking kind of knows what it is, and everything else. And then you construct an operator that's doable in terms of the gates I've described for you. That does this. When acting on the function, it's -1 to the function f, which distinguishes the number. Which means that when I apply this operator f to this totally balanced state, it's a reflection, and there is a reflection means that you subtract 2 times this scalar product, even though you don't know what this number is. That's what this operation does. And then you introduce another reflection, a reflection with respect to this balanced state itself. And it turns out that the combination of the 2 reflections, as you know, when you compose 2 reflections along axes which are at a certain angle, that means rotation by twice that angle. So this combination rotates your balanced vector by a certain angle, which is for big N is 2 over a root n, and it does rotate this balanced vector in the direction, everything happens in the 2-dimensional plane, which is a very nice part of this algorithm. It rotates it towards the sought unknown vector, and it turns out that you need to rotate it by pi over 2, which means that you have just so many steps, and this algorithm does this improvement of a classical algorithm. You have not O of n, but O of root n steps. Some quantum algorithms allow you exponential speed up, some don't. Exponential speed up is for the integer factorization theorem that you may have heard of. That's a story which divided into several steps, and a particular part of the algorithm you use quantum computer. It doesn't solve it directly. There are also trial and error, but still the trial and error is a lot better. It's not exponential depending on the number. Now I will skip the entanglement. So I will certainly not translate this back into English. Schrödinger, actually, that's from Schrödinger's letter to Einstein. Schrödinger's grandmother was British, so Schrödinger spoke good English since his childhood. So he invented the word Verschränkung, which is entanglement, and this is what? This is when you say, like beams, when you make a roof of a building, of a house, that's what Verschränkung is, when you tie things together. Entanglement may not be the best translation, but anyway. So I will just skip over these slides. The point is that when you have this maximum entangled state with a minus here, which is a kind of secondary but still very important thing because it's a singlet then, and you have Alice here and Bob over there, their measurement results are strictly correlated. So whenever Alice measures, she can measure any of the 2 things, but when she measures this one, this disappears. The wave function collapses to the first term, which means that Bob is automatically left with spin down, and when Alice, that's out of her control. She doesn't know what she's going to measure, but when she does measure spin down, that means that the wave function collapses to the second term, and Bob is automatically, even though he can be light years away, is automatically left with only one possibility. So the point is that there is not even dependence on the direction. Mathematically, there's a simple exercise in spin algebra that you can rewrite this as spin there, spin opposite, minus vice versa combination along any direction. So the direction can be, there is not even dependence on the vertical direction. It's only, it's implicit here, but it is not there. It's only the basis that I choose. It can be written in any basis. Which means that the spin of electron 2 can be predicted along any direction after spin of electron 1 is measured along the same direction. But you can choose the direction along which to measure after the entangled pair is created. So it's created, they are sent to Alice and Bob, and then someone tells them how to orient their Stern-Gerlach devices. So a good question is, how do they know that that's a canonical text from Schrödinger, that electron 2 is prepared to answer the question of its spin along vertical direction or along any other direction. His answer to any of these questions is correct. He shows up the spin which is opposite to the spin that had been observed for electron 1. But electron 2, as a pupil at an exam, as a student at an exam, cannot know which of the two questions about the direction, this direction or that direction, I'm going to ask first. It therefore seems that our student is prepared to get the right answer to the first question that he is asked, no matter what. Therefore, he must know both answers, but he cannot, because Sx and Sz do not commute. These are the spin projections along different directions are not commutative variables, so that's impossible. Einstein, therefore, in his paper with Podolsky and Rosen, concluded that either you have a spooky action at a distance, that somehow they shout, the first electron shouts to the other one across distance with superluminal velocity, what happened at the measurement, or spins along all directions are known in advance. They're not, well, that knowledge is of course not in quantum mechanics, not in wave function. Therefore, quantum mechanics is incomplete. And what happened in that, there was a paper by Einstein, Podolsky, and Rosen. Podolsky leaked the contents to New York Times 2 weeks or 3 weeks before the publication of the paper. Einstein never spoke to him again. And that is the title. Einstein Attacks Quantum Theory. It says scientists and two colleagues find it not complete, even though correct. But nobody, even those days, long before Twitter and everything, nobody really read anything beyond the title. So quantum mechanics can be incomplete. And at the same time, Einstein thought or believed that there is, what does it mean? It means that there are certain details behind what we know, behind the quantum mechanics as we know it, at a deeper level of organization of matter. And there will be no indeterminacy, no chance, maybe. That was Einstein's hope. So I will skip the details because they are really very boring. What happened is that John Bell, in the 1960s, he realized that no matter how you take an entangled pair and you assume that they know what this, and you keep doing that, one experiment after the other. At every experiment, randomly, somehow, they take a cheat piece of paper to cheat quantum mechanics, where every electron has a list of all his answers to any question about spin in any direction. And they agree on that cheat list every time. And it can change, that's on my previous slide actually, it can depend how everything is stochastic, so there is an unknown probability distribution depending on some unknown spin parameters. So if you are asked about spin in the long direction R, reply A with this probability, and the whole thing is controlled by some unknown hidden variables, hidden parameters which I have no idea about. And then what Bell invented, and he didn't live long enough to receive his Nobel Prize, is that you can find that they're cheating, even though you have no idea how they cheat, how the electrons cheat, what kind of arrangement they have between them. All you have to do is you no longer measure spin Alice and Bob, no longer measure spins along the same direction. What they have to do, they have to make a series of measurements with some non-parallel directions A and B, and take the mean value expectation, just the average, this just experimental results of Alice, result of Bob, and you just take the average. That's it. Then you do the same by changing the direction. Bob changed the direction, then Alice changes the direction, and then they both change the direction. So they have 4 series. And then what happens is that there is a particular combination of these numbers that you get from experiment. These numbers that you get from experiment, which can never exceed 2. That's called Bell inequality. This is CH, strictly speaking, Clauser, Horn, Shimony, and someone else. But still, many people call it. Tell me who? Who's the 4th guy? Oh, I thought someone knew. Hauser. It's still called Bell inequality because that's not what the Bell was not. The first Bell inequality was not of this form. But ideologically, this is along the lines of original Bell inequality. It can be measured. Okay, I'll skip the derivation. It's easy. It's very simple. And then you compute the same thing in quantum mechanics. You compute the same thing in quantum mechanics. That, of course, depends on the angles between your directions. And there is a certain arrangement when the angles reduce to a single one, and there is particular one, all are the same, and there is the most distant one, angle distant, there is 3 phi. And it turns out that the expression, the quantum analog of the same thing, can exceed 2 in a certain range, and the maximum in a certain range of angles, and the maximum is 2 times root 2, which means that quantum mechanics violates Bell's inequality by root 2 times. The same is for photons, and the thing is, of course, that Nobel Prize of 2022 is for the work that has been done over decades by several groups who kept measuring Bell's inequalities, violation of Bell's inequalities with increasing precision, closed loopholes, and everything. And we know that in nature we have this. We have this, not 2. So therefore, the moral is that entangled particles. So there could be 2 situations. One is entangled particles have some properties. We just don't know what these properties are. And we find out what they are when we make a measurement. Or they have no properties at all, which is difficult to imagine, really. When we don't know something, we tend to think that we just don't know, because how can you exist? It's not quite clear how you can exist without a property. If they had certain properties unknown to us, Bell's inequalities would have been satisfied. But they are violated, and that's experimental fact. So there is also example which is not appealing to statistic, which is GH-Z state. There's about the same story, but you have to have, it has also been tested experimentally. On my previous slide, you really had to collect some statistics. You really had to make sufficiently long series of measurements. Here is a single measurement does the job. It tells you that these 3, no matter how you create that entangled state of 3 electrons or 3 photons, and actually most of measurements with Bell inequalities were done with photons, but then on purpose they did some with electrons. And they cannot have any values. If they had any values unknown to you, that would lead to a contradiction. So there is a simple parity argument which also shows that assuming that in any given trial they have electron number 1, electron number 2, electron number 3 have particular values of spin, which we are unaware of, which are not known to us, leads to a contradiction. So just to finish with Wigner, Bell's technique was recently applied to Wigner friends experiment. You have two Wigners and two friends, and they received a entangled pair there. And it turns out that some very obvious things cannot hold simultaneously. Like, so there is a list of four. Let me rather show you the list of quantum observers. So people started thinking, okay, I asked my friend to be a quantum observer of the quantum world. What is the job description of an observer? What properties he or she has to satisfy? And it turns out that analysis shows that an observer must be local in space and time, never affects the past. That's important. If you can affect the past, everything changes. And your actions here are only local. You cannot immediately affect what's going on in Beijing. Any perceptions of an observer must be correlated with something in physical world. Like, for instance, when I see red color or when I see blue color, my brain reacts differently and then can be measured. As you probably know, that's easily done. They put something on my head and they measure. They can tell that I see different things. So observations must have correlations in physical world. Then there is what they call ego absolutism, which means I'm not in anyone's dream. I'm not anyone's dream. Everyone must proudly, addressing the world, must proudly say the existence of my own thoughts is absolute. It's independent of any context. It's just there. And then friendliness. A qualified observer considers reports of other qualified observers just as good as his own, which is a reasonable thing to do, of course. So these four properties are inconsistent in this way. They lead to something like Bell inequalities. And these Bell inequalities must be violated in quantum mechanics. A good question is, well, everyone believes that they are violated. Experimental tests are a little bit tricky because it has been tested, but to have something like something resembling an observer, you once again have to isolate from the world, from the outside world, from the environment. So what has been done so far, the role of an observer was of Wigner's friend. The role of Wigner's friend was played by a photon. Not everyone agrees to count a photon as your friend. Maybe you would really wish to have something bigger, a bigger friend. But so our only hope is to use a quantum computer. In an ideal quantum computer, what you emulate, which is not really the case, but what you emulate is as if it were no information is leaking to the outside world. It is as if it's isolated from the outside world. So in a quantum computer, sufficiently powerful quantum computer, you can probably realize the artificial intelligence, which would be tasked with the problem to measure state of some other qubits and then somehow tell us where the rupture of quantum reality occurs, what's going on there. So one of the use of quantum computers, one of the possible use of quantum computers, if and when they take off, really take off in the future, will be to study what quantum reality is. So my final statement is that quantum mechanics is actually, it's 100 years of quantum mechanics this year. So it sees its centennial in full glory and in full power, even though it still leaves behind the scenes a number of important questions. What the reality is, what ontology is behind the formalism. It's only a scheme for for assessing the results of experiments, whether there is an wave function collapse, what it's caused by, and what is governed by, what the reality, what the relation of the wave function with our three-dimensional space. Yes, we know if we say given some physical system, we know how to encode it in the wave function. If we're given a wave function, an entangled wave function of something, it's difficult to say what it describes, because it never describes one particle traveling here, one particle traveling there. The way from the wave function to our three-dimensional, the way from Hilbert space, if you consider Hilbert space the actual quantum reality, and David Deutsch's quotation in the beginning of my talk, then the way, the path from the Hilbert space reality to our three-dimensional reality is very tricky, and it's a challenge. And the relation to our classical reality, of course, because quantum world there inside us, it also induces classical reality. And of course, there's a famous David Deutsch statement that quantum computer is so powerful just because, for the single reason that it operates in several parallel universes at the same time. Whether or not that's the case, we have to see. So that's it. Thank you.
Sorry, could you clarify, so following this metaphor of having a deck of cards?
Yeah, I have a single card. In my casino, I have a single card, which doesn't have a particular value. That's what the wave function is about. So it looks like a single electron, but it lives in no particular point of space. So my card has no particular value.
Is there anyone who sees the hand? I mean.
Oh, that's a good question. No. Oh, good question. Thank you. No. No. Well, I can have probably I can have some idea, but. Well, look, any metaphor has to stop somewhere. For instance, I never tried to extend it as far as the Schrödinger equation, because what's governing, what's there instead of, in place of the Hamiltonian energy? No, you only see it when you ask to open up, to put it on the table, and then it becomes an ordinary card with a single value, with a particular value. But then Borner rule applies.
But can we say that electrons in this experiment with could you remind me on this inequality name? So
Bell's inequality?
Yeah, in Bell's inequality.
John Bell. Bell.
In the experiment with the entanglement, can we say that electrons somehow they know initially their hand of cards?
Oh no, they don't. If they know, then Bell inequalities would be yes. If they did, Bell inequalities would be satisfied. But the point is that Bell inequalities are violated, and that's damn proven experimental fact. So that's an important point. That's Nobel Prize 2.5 years ago. The previous slide contained a book. This is a book more for general public, but about quantum mechanics, which I suddenly became an author of, but rather unexpectedly. But it does discuss this and several other tricky points as well. So the metaphor is, of course, borrowed from over there. Thank you. That's it? Okay.
So you said that you cannot clone a wave function?
No. No cloning theorem, just because of the norm for unitarity. You easily see that unitarity forbids that.
But does that mean that you cannot create a superposition of two wave functions?
Well, you can copy it. Like, for instance, when you do teleportation, quantum teleportation, you do reproduce the given wave function over there at a distance. Nothing superluminal, but you can. But this one is necessarily destroyed. That's the point. So when you take a wave function and do something with it, in most cases, it becomes part of something else, but it cannot keep the same information intact in the way it was originally given to you.
But like superposition is a bit different thing. It's not, well, it's essentially you are copying, but also superimposing.
You mean what? You mean that error correction trick? Is that what you mean in particular?
I mean overall. Sometimes you read textbooks, and they, well, kind of
What you mean?
Create the image that you are able, like at the technical level.
Yeah.
If you have two-wave functions, psi1 and psi2,
Yeah.
you are able to produce.
Oh, you can. Well, Hilbert space is linear, so you can take a sum of two.
But can you do that? I mean, in practice, and be sure that what you produce is actually psi1 plus psi2.
I'm not sure. Let's think how we can do. How we can possibly do that. Tensor product is easier because it just applies to different degrees of freedom.
So in a way, it's like copying, but even more complicated. So this is possible to do.
Okay, I'll think about it. Thank you for the question. The no cloning theorem is not a big deal. It's just unitarity in the tensor products space. You have the space where you originally had the wave function. If you want to retain it in that, and then you want to have a copy in another tensor factor, you just see that norm is not conserved. Unitarity forbids that. It's an elementary result, actually. So maybe it doesn't apply to what you were saying. What you were saying is linear, and I think what you said is doable. What you asked about is doable. I'm maybe not able to tell you how you do that in more operative terms, but operational terms, but I think it's doable. It's not like you keep it and also have the same in a different tensor product of your Hilbert space. Copy the same in function that it's also reproduced on different another physical system or on different degrees of freedom or something. So in another tensor factor in the Hilbert space. So that's tensor product rather than linear structure for superposition. So thank you. Oh, the very last question.
Sorry, is there any certain evidence that the universe is linear? Is there any chance to
The universe is linear.
to live in a non-unitary situation?
Oh, we don't know what quantum reality is. Maybe some people argue that actual quantum reality is the Hilbert space reality. Then our three-dimensional space is an emergent thing. And they're trying to do that. There is an approach which tells you that you can kind of start thinking about space by that's crazy, by analyzing the wave function and through entanglement. More entanglement means closer, less entanglement means at a longer distance. So maybe even three-dimensional space is emergent, but we don't know. We don't know what quantum reality is. Is it a Hilbert space reality? Then this world is mathematical. I'm not sure that I'm ready to go that far.